What is a black hole? A black hole is an astronomical object with gravitational pull so strong that nothing, not even light, can escape from it once it crosses a specific boundary. These exotic cosmic objects represent some of the most extreme conditions in the universe, where matter is compressed to such extraordinary density that it fundamentally warps the fabric of space-time itself. Formation and structure. Black holes form when massive stars, typically those with more than 20 times the Sun's mass, reach the end of their lives. When these stellar giants exhaust their nuclear fuel, their cores collapse catastrophically under their own gravitational weight, triggering a supernova explosion that blows away the star's outer layers. If the remaining core exceeds about 3 solar masses, no known force can prevent its complete gravitational collapse into a black hole. The structure of a black hole consists of several key components. The singularity. At the very center lies a point of theoretically infinite density where all the black hole's mass is concentrated. This represents a breakdown of our current understanding of physics, as the extreme conditions cannot be described by known physical laws. The event horizon. This invisible spherical boundary surrounds the singularity and defines the point of no return. Once anything crosses this threshold, it becomes impossible to escape, as doing so would require traveling faster than the light of speed. The event horizon size is proportional to the black hole's mass. More massive black holes have larger event horizons. The interior space. Between the event horizon and singularity lies a region where space-time becomes severely distorted, creating what scientists describe as a very bad place to travel through. The concept of black holes emerges from Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of space-time. Black holes represent extreme solutions to Einstein's field equations, creating such profound distortions in space-time that they form deep troughs in the fabric of the universe. The Schwarzschild radius provides the mathematical foundation for understanding black holes. This critical distance, calculated as Rs equals 2gm over c squared, where g is the gravitational constant, m is mass, and c is the speed of light, determines the size of the event horizon for a non-rotating black hole. Any object compressed within its Schwarzschild radius becomes a black hole. For perspective, Earth would need to be compressed to just 8.8 millimeters in diameter to become a black hole. Astronomers classify black holes into several categories based on their mass. Stellar mass black holes range from about 3 to 50 times the Sun's mass and form from collapsed individual stars. Scientists estimate there may be as many as 100 million stellar mass black holes in the Milky Way alone. Supermassive black holes contain hundreds of thousands to billions of solar masses and reside at the centers of most galaxies. The Milky Way's central supermassive black hole, Sagittarius A, weighs approximately 4.3 million solar masses. Despite their enormous mass, these giants can have surprisingly low density. Some supermassive black holes have densities less than water. Intermediate mass black holes represent a recently confirmed category weighing between 100 and 100,000 solar masses. These objects bridge the gap between stellar and supermassive black holes, though their formation mechanisms remain poorly understood.
Observing the invisible. Since black holes trap light, they cannot be observed directly. Instead, astronomers detect them through their gravitational effects on surrounding matter. When a black hole pulls material from a nearby star, this matter forms an accretion disk that heats to millions of degrees and emits intense X-ray radiation. Scientists also study the orbital motions of stars around invisible massive objects to infer the presence of black holes. In 2019, the Event Horizon Telescope achieved a historic milestone by capturing the first direct image of a black hole's event horizon, the supermassive black hole in galaxy M87, located 55 million light-years away. Black hole evaporation. Contrary to popular belief, black holes are not eternal. Stephen Hawking's groundbreaking work revealed the black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly evaporate over time, with smaller black holes radiating away faster than larger ones. The evaporation process creates a fascinating paradox. As a black hole loses mass, its temperature increases exponentially, causing it to radiate even more rapidly until it eventually dissolves in a violent burst of energy. However, for stellar mass black holes, this process takes an incomprehensibly long time, approximately 2.14 times 10 to the 67 years. Recent research has expanded our understanding of black hole evaporation, showing that the curvature of space-time itself can create radiation even far from the event horizon, suggesting that all massive objects in the universe will eventually evaporate.